Okay, good evening, everyone. It is a privilege to introduce you to our center, the Center of Advanced Studies and Innovation Lab, in short, CASI Lab, located in Silchar, Assam. Since beginning its journey in 2018, CASI Lab has been working to develop a conducive research ecosystem in the sciences, primarily focusing on mentoring project-based studies for undergraduate, postgraduate, and research students, as well as organizing a series of in-person and online talks. We are firmly committed to providing a democratic, borderless ecosystem that bridges the gap between institutional experts, independent scholars, and grassroots researchers by facilitating collaborative projects, regardless of geographical constraints. As we proceed with today's seminar, I invite you to view our modest efforts through the lens of CASILab for the greater good. We are truly honored to have with us an eminent physicist and a distinguished academic, Professor S Lakshmibala, as our speaker for today. Professor Bala is a former senior professor at the Indian Institute of Technology, Madras, and has made significant contributions to the field of quantum optics and quantum information science. Over the years, our research has spanned a wide range of topics, including quantum state reconstruction, optical tomography, and foundational aspects of quantum mechanics. She is also associated with the Center for Quantum Information Communication and Computing at IIT Madras, where she continues to contribute to advancing research in quantum technology. Her work has been widely recognized for its depth, clarity, and impact on both theoretical understanding and experimental relevance. Today, she will be speaking on the topic optical tomograms and quantum states of light. So, ma'am, it is over to you. You can start.
Thank you very much. It's a pleasure to talk here. First of all, it was a pleasure to be a member of Q Connect because I could listen to a very diverse set of talks for which information was put up there. And it's a pleasure to hear and learn about CASI Lab and the kind of outreach work that is being done there. Thank you very much for this invitation. I have been interested in tomograms, both optical and spin tomograms, for close to 2 decades now. So I have a lot of slides, but I'm going to keep this very open-ended. I will go as far as I can go in the time that is given to me. If there is any particular interest in some details, I might want to go into it. But my aim is to give you a broad picture, emphasizing the beauty of tomograms in general. Several very important physicists who have made pioneering contributions have worked on tomograms, quantum tomograms and classical tomograms. There are lovely papers by Professor Manko, Igor Manko from Lebedev and his collaborators. And then there are nice collaborative papers between Manko, Sudarshan, Marmo, and others. Very nice mathematical formalism. And in fact, it's a very good way of trying to see how you can have a common framework to study both aspects of classical physics and quantum physics. In fact, that seems to have been the motivation for all these people. I start with what you see on the screen. Schrödinger made no secret of his intention to substitute simple classical pictures for the strange conceptions of quantum mechanics, for whose abstract character he expressed deep aversion. Now, I've taken this statement from Rosenfeld's selected papers. So there has always been this idea, right, that you want a common platform, a framework where you can give a very broad picture And then you can narrow in on whether you're looking at classical, aspects or quantum aspects. That seems to be the central theme of these people's work. So there are different approaches to understanding the quantum classical divide. Now, an ideal framework for investigating the classical quantum links, the overlaps, the differences, etc., is optics. The common thread is this. Probability theory is extensively used in classical settings, and quantum mechanics is inherently probabilistic. However, different states of light are distinguished by distributions such as the Wigner function, which is quasi-probabilistic. That means that if you plot the Wigner function as a function of x and p, it could be negative for many states of light in some regions of the XP plane. The interpretation of x and p, as we will get to later, is that x and p are field quadratures, not position and momentum when you're talking about optics. I will certainly explain that part, in particular for students here and for people coming from areas where quantum optics is not a very familiar subject. So the idea is this. Suppose you identify a probability distribution or a collection of probability distributions, which is essentially the tomogram. These are not quasi-probabilities, just blue-blooded probability distributions, and attempt to understand different states of light. We can see differences between the classical and quantum approach. So the tomogram itself is made up of data available from measurements. You get data from measurements, you bin it into histograms, and this constitutes the tomogram. I will show you different tomograms as I go along. So if the measurements pertain to light, they provide the optical tomogram. If it pertains to spins or qubits in general, you will get a qubit tomogram. An example of a tomogram is simply a medical scan. That's an example of a tomogram. Suppose you want to scan somebody's brain. So you're going to zero in on some angle, take the intensity profile of the brain at that angle. That creates a tomographic slice for you. Then you move on to the next angle and do the same thing. So you get a complete picture of what is happening in the brain. And suppose that at some value of the angle, you find that something is going amiss in the brain, then the doctor will, demand more slices nearby that angle to see what is happening. So a tomogram is like that, at different angles, and in particular in the optical tomogram, in particular in the quantum optics setting, you're merely going to ask for, if you have an unknown state of light, you're going to ask for modulus of psi the whole squared as a function of the distance, as a function of x. You won't call it the distance anymore. You will call it the field quadrature. But basically, you're going to look at probability density functions at different angles. And from there, you're supposed to reconstruct the state of light. So an output image is obtained at different angles. Each image is a slice of the full tomogram, and each image therefore carries partial information about the object. The full state is to be reconstructed from the set of all slices. Now, one of the main problems in quantum mechanics, which was addressed by Pauli initially, was this. Suppose, forget the tomogram. Suppose I give you modulus of psi of x the whole squared. And of course, its Fourier transform, psi tilde of p, its modulus the square alone. Can we reconstruct psi of x and psi tilde of p? So from the densities, can you reconstruct the state? The answer is the phase information is lost in the probability densities. All right. But there is a nice way of extending this argument. And this was given by Reichenbach in his book, philosophy of quantum mechanics, I give you two wave functions, psi1 of x and psi2 of x. Those are put down there. N is a normalization constant. And the two wave functions are explicitly put down there. Now, correspondingly, I can get psi1 tilde of p and psi2 tilde of p. These two states, these two wave functions have been given for you, and you can check that modulus of psi1 of x the whole squared equals modulus of psi2 of x the whole squared. Similarly, you can check that modulus of psi1 tilde of p the whole squared equals modulus of psi2 tilde of p the whole squared. Now you may imagine that these two states, if you find the overlap and mod square, the fidelity, as that is called, should be unity. Because it looks the same in x, it looks the same in p. So they should be off at most by an overall phase, and the fidelity should be unity. Not so. This is an example where the fidelity turns out to be what I have put down there. Alpha is a complex number, alpha plus alpha star by the denominator, twice root of alpha alpha star. This is not unity. So clearly, if you want to check if two states are the same, it is not enough if you just look at two canonically conjugate, operators like position and momentum. It is not enough if you just look at x and p. You have to do more work. Therefore, you need to go beyond just two quadratures, x and p, and look at many more. You need more angles. You need to look at a tomogram. So in practice, however, only a finite number of slices can be obtained. In principle, we may need an infinite number of slices to reconstruct the object. Now, several questions arise. What is the optimal number of slices needed to reconstruct the object? Now, this comes under the area of state reconstruction from the tomogram. Now, the number of slices depends on the system considered. That is common sense. Even in a medical scan, sometimes you do 60 slices, sometimes you do 120 slices, sometimes much more than that. Question is, can there be any favored set of slices? Maybe the canonically conjugate variables. Now, if you need a large number of slices, can we avoid detailed reconstruction of the object and infer its properties from a finite set of images, like you do in a medical scan? So these are the kind of questions that are raised. And if you look stepwise, you get the experimental data, which I said is the PDFs, the probability density functions at various angles. You bin it, you get the quadrature histogram, and you construct the optical tomogram from it, and I'll tell you how you go about it. Now you have two options. From the tomogram, you can directly get the Wigner function or the density matrix. The density matrix is really the state of the system. This procedure is a statistical procedure. In the experiment, you get some final state. You start with some, choice state of yours, and then you have to do some maximal likelihood estimates, and so on. Now, this adds to more errors over and above the experimental errors that were there when you got the data. It's inherently error prone, and you would find that in this area, experimenters more or less rejoice if they can, identify a state with 60% probability and so on. So it's a tough job. This is not the situation when it comes to qubits and spin halves and all that. And as I proceed, I'll tell you why. So at least as far as quantum optics is concerned, state reconstruction is not easy. These days, many machine learning tools are used for that. Things become worse if you're going to consider, the radiation field or quantized light. propagating through a nonlinear atomic media. Then at each instant of time, the state is going to be very different. Of course, it's unitary evolution, but the state is going to be very, very different because of the nonlinearity in the system. Then at each instant, if you want to recognize what the state is, you're going to have many, many tomograms, one for each instant. And in each case, you have to reconstruct the state. Now, that's a very arduous task. You would certainly try to use some other procedure wherever possible. And that is shown here. The other method is you start with the optical tomogram and you read off as much information as possible directly from the tomogram about the state. In other words, you try to characterize the state just from the tomograms. So while I'm supposed to also be working in quantum state reconstruction, my talk today is about how do you circumvent state reconstruction. This is called the tomographic approach. You would like to understand the state just from the experimental data, from the tomograms. Sorry. I need to digress now because I understand that there are people here who are not very savvy about quantum optics. You see, this is particularly for the students here. Quantum optics can be introduced in the following manner. Students are familiar with the quantum simple harmonic oscillator. It has equally spaced energy levels. You would perhaps label the levels in the Dirac notation as ket 0, ket 1, ket 2, ket 3, and so on. And then you have these operators, which are the ladder operators, A and A dagger. In the case of the simple harmonic oscillator, the Hamiltonian was x squared by 2 plus p squared by 2. Of course, I have set h cross m and omega to be 1. It's a quadratic form. Now, there is another situation where the energy density is quadratic, and that is E squared plus B squared, the electric field and the magnetic field. And the Hamiltonian density, apart from epsilon naught and mu naught and so on, which I set equal to 1, it is E squared by 2 plus B squared by 2. So when I quantize the electromagnetic field and get photons, I can simply take the mathematics of the quantum simple harmonic oscillator and use it to describe photon creation and destruction. So instead of x, I have E, and instead of writing x in the oscillator case as A plus A dagger, give or take a constant, I will now write E as A plus A dagger. And instead of writing P as A minus A dagger by I can write B, the magnetic field, as A minus A dagger by I. The commutation relations A dagger equals identity go through. The interpretation, however, is different in optics. In the case of the oscillator, there was a single simple harmonic oscillator, and A and A dagger took you between the energy levels of that oscillator. And A dagger A itself, its eigenket n, had an eigenvalue, little n, which told you that you're in the nth level of the oscillator. So A dagger A on ket n is n ket n. In the case of optics, you move on with the same model to multi-photon creation and destruction. Ket 0 would now represent the 0 photon state, ket 1 the 1 photon state, and so on. And A dagger A would be interpreted as the photon number operator. You would no longer refer to x and p as position and momentum, but as field quadrature operators, given there as A plus A dagger by root 2 and A minus A dagger by root 2i. I can construct several interesting superpositions of the ket n's, that is a 0 photon state, 1 photon state, and so on. Ideal laser light is the standard coherent state, or CS, and I have put that down there in blue. I call it ket alpha. Alpha is a complex number in general. And you can see that it is an infinite superposition of the 0 photon state, 1 photon state, 2 photon state, and so on. Now, like any other coherent state of light, coherent state of the oscillator, it satisfies the minimum uncertainty product in the field quadratures. If I set parameters and the Planck's constant to 1, then delta x squared equals delta p squared is half. Now a state is squeezed in x if its corresponding delta x squared is less than half. Of course, then delta p squared should be greater than half to satisfy the Heisenberg uncertainty principle, or better still, the Schrodinger-Robertson uncertainty principle. And a state is squeezed in P if delta P squared is less than half. So coherent light gives you the reference state. I'll be perfectly happy if you can interrupt whenever you want and take on any questions. There are simple examples. The coherent state is called a classical state. There are good reasons for that, and that we need not get into that now. But there are simple examples of non-classical states. One is the photon-added coherent state. So I have defined it there as ket alpha comma m, where that's an m photon-added coherent state. So you use the photon creation operator a dagger m times on the coherent state alpha and normalize it. Turns out that the m photon-added coherent state is an eigenstate of a nonlinear operator defined there, capital A. And therefore, it is sometimes referred to as a nonlinear coherent state. Now, these states have been produced in experiments. At least the single photon added coherent state is pretty much there in experiments. It's been produced and identified by state tomography. I return to the Pauli problem. So as Rosenbach proved, you can't just work with the x and the p quadratures. You need to make measurements at various angles. So you define the rotated quadrature operators given by x sub theta, which I have given you there. It's an a dagger e to the I theta plus a e to the minus I theta. So what is the tomogram? So without making a mystery of it, you define your tomogram, w of x theta theta, as the expectation value of the density matrix for given theta in the state x theta theta. So when theta is 0, actually, it is like the position representation, and when theta is pi by 2, it is like the momentum representation. But you now call it the x quadrature and the p quadrature because you're talking about fields. Now, at least for a pure state psi, the density operator is given there. It is ket psi bra psi. And hence the tomogram is simply psi of x theta theta, the whole squared. And you do this for different thetas and the corresponding x thetas. So you're measuring PDFs along different angles. Now, for every theta, you have a complete basis. You set theta equal to 0. And again, for the students, if you set theta equal to 0 in the oscillator problem, you had x. But then you see x forms a complete basis. Ket x forms a complete basis. Like that now, for every theta, you have a complete basis x theta. And how do I get from x, from ket x, how do I get ket x theta theta? I do a unitary transformation. I do e to the I theta a dagger a. So a homodyne detection experiment is what is done in the laboratory to obtain the probability density function mod psi of x theta theta the whole squared in different quadratures. Now, once you do this experiment and get it at various quadratures, you stack them up to form the tomogram. So I've given you some tomograms here. You plot x theta on the x-axis and theta on the y-axis. Theta going from 0 to pi by 2 takes you from the x to the p quadrature. And pi by 2 to pi you get back. But I have plotted it to 2 pi deliberately along the vertical axis just to show you the symmetry properties. There are some symmetry properties in a tomogram, and you see that there. Look at figure A. That is the optical tomogram for the coherent state, ideal laser light. You have a color code, and that is basically your profile, the mod psi of x theta theta, the whole square. And the red means high intensity, high probability density, and the blue, the violet, means low. From the tomogram, you construct the Wigner function, as I pointed out, and you get this Gaussian Wigner function for the coherent state. While usually Wigner functions have some negative regions in the XP plane, this one doesn't have it. And below in figure C, I have given you the optical tomogram for the even cat state, or the even coherent state, which is the superposition of two coherent states with a relative positive sign. And in D, I have given you the tomogram for an odd coherent state, which has a relative negative sign between the two states. And I have chosen for my purpose mod alpha squared equals 0.5. Now, for those of you who want to know what is the physical significance of this mod alpha squared, it is the mean photon number. Because if you sandwich the photon number operator A dagger A between ket alpha and bra alpha, you would find that the answer is mod alpha squared. So it is really the intensity of light. So if I want to recast Pauli's question, do the tomograms X rho X and P rho P. I'm not giving you the full tomograms. Basically, I'm just looking at the X and the P quadratures and finding the density matrix expectation values. Does that not suffice to reconstruct rho? Those are just the diagonal elements of the density operator for theta equals 0 and pi by 2. That's not enough, which is the answer to Pauli's question. And that is why the homodyne detection. Now, one should remember that after state reconstruction, there is just a single density operator rho, which has all information about the state. But before state reconstruction, you need several tomographic slices, and all these slices contribute to reconstructing the state. Now, an explicit expression connecting the full density matrix, the one that you get after state reconstruction, to the optical tomogram, which you have before state reconstruction. That expression is given, for instance, in this very nice paper by Mancini, Manco, and Tombesi in 1997. So you have to integrate over an infinite number of tomographic slices in order to get suitably, not just a blind integration, suitably weighted to get the density matrix or the Wigner function. Now, this is an important point. By the very construction, you see rho is the Hermitian operator, and you're just getting its expectation values. So hermiticity of rho is assured. And because there is a completeness in every basis at every angle theta, the integral of the tomogram for over an x theta, given a value of theta, is 1. That is just the completeness statement. That is not enough to guarantee that the reconstructed density matrix is non-negative. This is going to be an important matter. Hermiticity is assured, completeness of basis states for every theta is assured by construct. But you have to check if the reconstructed density matrix shows positivity. Now, I can't reconstruct. I don't want to reconstruct. That is precisely what I wish to avoid. Then what do I check? I will have to check that the Schrodinger-Robertson uncertainty relation, recast in terms of tomograms, this must be satisfied for it to be a quantum tomogram. Else it is not a quantum tomogram. But you see, I have a common framework. I've set up a method by which you can take an experiment where you will get classical intensity profiles like in medical scans. And in that same framework, I can look at quantum optics, where I find PDFs. And then I worry about whether it's a quantum tomogram or a classical tomogram, avoiding state reconstruction by simply checking if the uncertainty relation, the Schrodinger-Robertson relation, is satisfied. This is an important matter. Now, from the tomogram, what can I compute? Well, certainly I can compute variance of x theta and all the higher moments of operators for a fixed theta in a straightforward manner from the tomogram. I'm going to, when I say tomogram, from now on, I mean optical tomogram. So you can compute the squeezing properties. Now, this does not mean that all I need to do is, if I worked with 30 angles, I find the variance of x theta in all those, corresponding to all those 30 angles, and individually check that Schrodinger-Robertson is satisfied. No, that's not the way you go about it. And those details I have with me, and I can get to that if anybody is interested. It's not as straightforward as simply find the variance in each quadrature. No. Because we need to remember that the density matrix comes after integrating over all the slices of the tomogram. And with that density matrix, you're going to find the variance in the reconstructed state. Therefore, before reconstruction, you can't simply find a set of variances, one for each quadrature. You have to do a proper integration, recast the Schrodinger-Robertson uncertainty relation in the language of tomograms, and check it. And the procedure to get these variances obviously depends a lot on expectation value of a dagger to the k, a to the n. And the expression is given here. And this is given in Wunsch's paper in Fitzroy 1996. Tomographic reconstruction of the density operator from its normally ordered moments. But you can see right here, in order to calculate a moment of order k plus L, if you look at the part in the equation on the right-hand side, the integral minus infinity to infinity, you see m pi by k plus L plus 1. And then there is a summation of m from 0 to k plus L. So, in order to calculate a moment of order k plus L, I need to consider k plus L plus 1 slices of the tomogram. So k plus L plus 1 probability distributions corresponding to those chosen values of theta have to be used in order to calculate the squeezing parameter from the tomogram without resorting to detailed state reconstruction. It may seem complex, but state reconstruction is much worse in optics. And the reason is simple. You're dealing with an infinite dimensional Hilbert space. Take, for instance, the coherent state of light. As I showed you in a couple of slides earlier, het alpha is an infinite sum of photon number states. So you're spanning an infinite dimensional Hilbert space. And that is going to make state reconstruction a very challenging job. Therefore, more the reason why you should try to read off as much as possible from tomograms. Already some things can be seen. You can get the squeezing properties of the unknown state, whose tomogram you have. You can check the variances and all the higher moments, so you can characterize the state. Of course, you can compute the mean photon number corresponding to that state. You just have to set k equals 1 and L equals 1 in that expression that is put down there, and compute it in the tomogram. So you have a lot of answers straight from the tomogram without adding to already existing experimental errors with state reconstruction errors. What else can you capture from the tomogram? For instance, if there is a wave packet, a Gaussian wave packet of light, propagating through what we call the Kerr-Hamiltonian, which is the simplest example of a nonlinear atomic media. The effective Hamiltonian is put down there. I have set H cross equals 1, and chi is the third order nonlinear susceptibility. Then you can write an effective Hamiltonian like this, taking into account the effect of the atomic medium on the electromagnetic field. So the Hamiltonian is written just in terms of the photon extraction and creation operators. It turns out that there is a revival phenomenon, which one has experimentally seen in many contexts. You started with an initial, let us say, Gaussian wave packet of light. At a time which we will call revival time, which turns out to be pi by chi, and therefore adjustable, the wave packet will return to its original form, apart from an overall phase. And therefore, if you compute the fidelity, that will be 1. So I start in my look at the tomograms. In figure A, which is the left side top corner, I start with a coherent state of light. Now, at time t rev, it becomes the same tomogram. Now, if you look at C before B, the bottom panel, at t rev by 3, you have actually 3 subpackets. It turns out that it will show up as 3 Gaussian subpackets. Of course, one-side version, because you want to preserve normalization of the state. But you will see it in the tomogram. You can see that there are 3 strands in the bottom panel which are cutting each other. And then at t rev by 4, if you look at figure B in the top right panel, there are 4 strands intersecting each other. In fact, the points of intersection are worth knowing, because when you reconstruct the Wigner function, they will show up as what is known as subplanckian structures. But that's not what I'm getting into now. And modulus of alpha squared, for my purpose, I've chosen chi is 1, and mod alpha squared equals 10. Always x theta is along the x-axis, and theta is along the y-axis, some scaled version possibly. And the tomogram is the plot W of x theta theta. So apart from what happens at revivals and fractional revivals, you can also capture qualitative changes in the tomogram near revivals, as in a medical scan. You see, if you look at the top panel is the tomogram, and this is the coherent state propagating in a Kerr medium. I have chosen mod alpha squared 49 and chi equals 1. Now, in the top panel, look at the middle tomogram. That is the way the tomogram looks if you plot from 0 to pi at 2 subpacket fractional revival. There are 2 strands and they will intersect each other. Now, just a little before that, at this instant minus epsilon, where I've chosen epsilon to be 0.005, you see the tomogram. The intersection happens visibly, not at the edge. Similarly, at epsilon after t rev by 2, the intersection happens visibly, but now towards closer to pi. So this is the top panel, and you can see qualitative changes even here. Now, if you do reconstruct the Wigner function, which is trivial in this case, look at the qualitative changes in the Wigner function. What turns out to be some 3 blobs in the center panel, bottom center panel, vertical blobs, now become inclined a little before and a little after. The Wigner function for seeing these changes, you can see it in the tomogram itself. In a very different context, where we have worked with the double well Bose-Einstein condensate. Again, if you started with the condensates in the 2 wells, macroscopic coherent condensates in the 2 wells, given by ket alpha, factored product ket beta, or ket alpha, factored product ket alpha, you see the revival phenomenon. And at t rev by 4, you have the top leftmost corner, you have 4 blobs. T rev by 3, the top right corner, you have 3 blobs. T rev by 2, it turns out that the values of alpha are not enough to keep them distinctly away. So there is a merging, but actually there are two blobs which have superposed on each other. And T-rev is a single blob. So at instance of full revivals, as I have said, the overlap mod squared will be 1. Theoretically speaking, experimentally, there will be some errors, but the fidelity will be close to 1. And fractional revivals occur at KT-rev by L, where K and L are integers. And these are the tomograms in this case. The slices that we have used, you will see that since it's a double well condensate, it's a bipartite tomogram, and x theta 1 is along the x-axis and x theta 2 is along the y-axis. And I define bipartite tomograms later. So before we proceed to bipartite tomograms, let us reconsider the results by Manco et al. About an infinite number of tomographic slices being needed. Well, actually, in this Bose-Einstein condensate example, we only use 25 slices. But questions can be asked. Are 25 slices enough? Are they to be uniformly spaced in theta? So this becomes a pattern comparison problem. Comparing what patterns? You have to compare probability density functions for a fixed theta between two tomograms. But the tomogram itself, the way it is defined, it's a classical object, in the sense that all your probability distributions are good probability distributions. There is nothing quasi-probabilistic about it. So you can use classical quantifiers. And in classical probability theory, there is a very rich history of how to compare two probability distributions. So you want tomographic markers which are directly computable from the tomogram, with which you obtain the distance between two PDFs. Now this becomes important in photon addition and subtraction to a reference state, and very useful for recent experiments, because if you're looking at a coherent state or a squeezed vacuum state or an even coherent state, then if you add or subtract photons to them, you can compare the tomograms between the reference state, whichever it is, and the new tomogram that you get after addition or subtraction. And you must be able to at least tell us something about the nature of photons that are, the number of photons that are added and so on. So there are different tomographic markers. One is called the Bhattacharya distance. So if you have two PDFs, P of x and Q of x, you define a Bhattacharya coefficient, which is integral over dx of root P of x, Q of x. The Bhattacharya distance between the PDFs is minus log of this coefficient. Now, this does not obey the triangle inequality, but it's a symmetric distribution between P and Q by its very construct, in contrast to something else called the KL divergence or the Kullback-Liebler divergence. The KL divergence is the statistical distance. It is not symmetric in the two distributions. It's not metric. It does not satisfy the triangle inequality, but it can be interpreted in terms of information entropy. Relative entropy 0 implies both distributions have the same information content. For continuous distributions, you can define, or rather it is defined in the literature, this DKL is integral P of x log of P of x by Q of x dx. That P of x is your reference distribution. Now this can be infinity, this KL can be infinity. Example, if you take P of x to be the Cauchy density and Q of x to be the normal density, then you can check that KL is infinity. But then there is another distribution. It's called the Wasserstein distance. You consider two normalized PDF f of x and g of x with corresponding cumulative distribution functions, capital F and capital G. The Wasserstein distance, you can actually define a P Wasserstein distance. I'm not getting into that now. More accurately, the one Wasserstein distance between f of x and g of x is given by equation 1 here. It is simply modulus of the difference between the cumulative distributions, integrated from minus infinity to infinity, because my x goes from minus infinity to infinity. It's called the Eichner's distance. It is the optimal cost of reshaping f of x into g of x. The cost is defined as the integrated probability mass, which is shifted, times the distance. That's why it's called the earth mover's distance. This is basis dependent, as I will demonstrate later, but it is symmetric. And it's a genuine distance measure in the space of probability distributions, as equation 2 tells you. The triangle inequality is satisfied. So this is the optimal cost of reshaping the pile of earth, and therefore called the earth mover's distance. Normally, we have been using, and in the literature, most people keep working with the KL divergence or the Wasserstein distance or the Bhattacharya distance. Each comes with its own advantage. And depending on the context, you would prefer one over the other. So if I take the photon number basis, this is just an illustration. The Wasserstein distance between the 0 photon state and the n photon state. I can compute it from the respective CDFs. In the X quadrature alone, I'm computing it. And I've plotted W1 versus N for the ground and the nth excited states. The leading large N behavior goes as root N. You can expect this on physical grounds because in the ground state, most of the probability mass in the state is concentrated around x equals 0, whereas in the nth state, it is concentrated near the classical turning points for both even and odd n. So the earth mover's distance from g0 of x to gn of x is root n asymptotically. It is basis dependent. We have this result in the photon number basis. For the same problem, if I work with DKL or the Bhattacharya distance, they don't go as root n asymptotically. It's of the form a times log n plus b. So you see, it's only logarithmically dependent on n. Hence, in this problem, the Wasserstein distance is a much more sensitive quantifier than the KL divergence or the Bhattacharya distance. But as I said, it depends on different settings, which is a better probability, better tomographic marker. Now I go to optical tomograms of bipartite systems. You define two rotated quadrature operators. You find that for entanglement, the KL divergence and the Bhattacharya distance fare better. So instead of a single tomogram, you have a bipartite tomogram, x theta 1, x theta 2, and you simply use the same definitions, except that you have an A and A dagger and a theta 1, and you have a B and B dagger and a theta 2. So this constitutes a quorum for theta I. And for each theta, you have a complete basis as before. So you have the two-mode density matrix, which is a function of x theta 1, x theta 2, theta 2. That's going to be the two-mode full density matrix, its expectation value in this set. And this again was originally the extrapolation to bipartites, to the best of my knowledge, was done by Manco and Coronel. I give you here an example. The bipartite model I have considered is an atom interacting with a radiation field. The reference is Agarwal and Puri's paper, which I myself was very fond of. It taught me a lot of things. And the Hamiltonian has a field dependence, which is just A dagger A. H cross was set equal to 1. The atom is modeled as a multi-level, infinite level oscillator. But it's a nonlinear medium, so there is a gamma B dagger squared B squared, and there's omega naught B dagger B. And the interaction is a simple interaction, what we call the beam splitter type interaction. There is an interaction strength G between the field and the atom. That's A dagger B plus AB dagger. It is not true that there are revivals automatically happening in bipartite systems under very specific conditions. And Agarwal and Puri have actually worked out the conditions analytically. That's a very nice paper, as I said. You find that there are really entanglement. Initially, the state is, you take a state, look at the bottom line in this, below the figure, in the captions. Let the atom be in the ground state and the field be a 5-photon state. Look at figure A. You actually find it's a factored product. So the entanglement is 0 initially, but of course they get entangled. And then you see entanglement dips. It's almost like you see a fractional revival at half time, which is somewhere between 200 and 400. And then at 1/3 time, there is a 3 subpacket revival and so on. And then a little past 600, it periodically revives. Not so in case B, there is real sensitiveness to the initial state, because if the initial state of light is a coherent state, then that is not true. And you find that there is a saturation and you don't see these entanglement dips. You don't see these revivals in entanglement. And I have plotted the subsystem linear entropy, which is what one uses as an entanglement quantifier usually. And the subsystem, this is the subsystem linear entropy that has been plotted. The subsystem linear entropy, look at the definition down there. It depends on rho. You have to reconstruct the density matrix in order to define the subsystem linear entropy. The question is, can you get tomographic entanglement indicators? This whole business of reconstruction, I'd like to bypass. Now, before I get to tomographic entanglement indicators, I give you here how near revivals there are sudden changes. Look at this. There are sudden changes in entanglement, and that is captured in optical tomograms. If you look at the top panel, that is for the original state where there was entanglement and fractional revivals and so on of entanglement. You see, at time 625, scale time 625, look at the top middle panel. That is the tomogram. You see 5 vertical black cuts because it revives. It has become a 5-photon state. With every photon addition, you will see that there is a cut. The cut is because of the zeros of the Hermite polynomial. Or if the wave function has the Hermite polynomial plus other weighting factors, it is the zeros of the wave function for every theta. So that is where the intensity becomes 0. So this is a 5-photon state. But just a little before that, look at the tomogram, top panel A, and a little after that, top panel C. Similarly, if you started with a coherent state, that's the bottom panel, at 1269, scale time 1269, look at the tomogram. Just a little bit before, you find that the tomograms look very different. So certainly sudden changes in entanglement can be captured. I want to make the following statement. So if you start with the squeezed vacuum or the coherent state of light, and if you add a photon, a single photon, you will have a single vertical cut. You add 2 photons, the black will go, and it will become, that same cut will have bright intensity. You add 3 photons, that cut, there will be 3 black intensities and black in intensity and so on. So you can actually look at the tomogram and say whether you have added an even number of photons or an odd number of photons to the state. These days, there are a whole lot of experiments happening in photon addition to light, particularly squeezed vacuum, even cat state and so on, because it increases the non-classicality of the state. And people like non-classical light for various reasons. So you see, this is simply the parity of the Hermite polynomial that's coming up. And that is reflected in the tomogram. So very useful from an experimental point of view. So that is what I have said here. So depending on the location of the bright and dark pattern, we know whether an even or odd number of photons are added to the reference light. In fact, we have 2 papers. Efficacy of tomographic markers and photon addition to coherent state of light. And we have compared it with experiment. What is the comparison? In the experiment, they did a conditional addition of photon. They reconstructed the state. They obtained the manner in which the fidelity changed with the parameter, like alpha. Whereas we did it all from the tomogram. We used the Wasserstein distance, the Kullback-Leibler divergence, and so on, and showed that the same trends are captured. So this paper addresses the advantages, spelling is wrong, of working with any of the 3 tomographic markers. Comparison with the recently published experiment on photon addition to coherent light establishes the advantage of working with the tomographic approach. This experimental paper with which we made comparisons is given below. It's the experimental preparation of multi-photon added coherent states, which was published in 2024. The next paper I drag your attention to is optimal sensing of photon addition and subtraction on non-classical light. We had the pleasure of collaborating with Professor Panigrahi and his student Arman in this paper. And this PRA paper addresses the several advantages of working with the Wasserstein distance in the context of addition and subtraction of photons. And you use this distance as the optimal tomographic marker to estimate photon number changes. Kulbach, Liebler, and Bhattacharya don't perform as well as Wasserstein in this context. We have extended this to a lambda atom interacting with two radiation fields. I want to now define entanglement indicators, and I believe my time is perhaps running out. I seem to have 5 minutes, and that should be enough for me. So if you look at mutual entropy, if you look at the last line, mutual information for discrete distributions. You have two distributions. If you have P of, the marginals are P of X and P of Y, and you have a P of X comma Y, which is the probability distribution of two variables. Then the mutual information is defined as P of X comma Y log P of XY by P of XP. So if there's a factorization, the numerator and denominator, you see, they cancel out and give you log 1, and that's nice. But you will, if you recall, the Kulbach-Liebler divergence is simply that for continuous variables. So you take the joint probability density, Pxy, P sub xy. Then you have the marginals, P of X and P of Y. And then you define DKL. You don't have to define it. It's already defined. It's simply the mutual information. But you will use this definition since these optical tomograms are continuous probability distributions. Use it in the quantum context, and you already have an entanglement indicator. You could define other entanglement indicators. I'm not going into that now for paucity of time. And we have looked at the extent of entanglement, sudden death, and so on in different platforms. For instance, we have worked with the double James Cummings model. There are two two-level atoms, A and B. A is entangled with a state of light, let us say C. B is entangled with a state of light, let us say D, but A and B are not entangled initially. Then you have the Hamiltonian. Of course, everything gets entangled with everything else during time evolution, but entanglement abrupt death or sudden death is seen at a later time. So you treat, it's only a two-level atom, you treat each atom as a qubit. So when you move from the excited state to the ground state in this two-level atom, each field loses one photon or gains one photon during the dynamics. So you treat each field as a qubit. So it's a one photon or zero photon qubit. It's a excited state or a ground state qubit of the atom. If you do the equivalent circuit of this optical system and process it in the IBM platform and determine the extent of entanglement from the tomogram itself, because we have tomographic entanglement indicators. I'm just giving you an example, extent of entanglement at one sample instant. The experiment and the simulation in the IBM and the numerical calculation agree very well. Experiment doesn't agree with the simulation in IBM because there are experimental errors and we didn't account for the errors. But the simulation in the IBM and the numerical calculation using the tomographic entanglement indicator agrees very well, 0.2311 and 0.2310. The first is due to experimental losses. We've also looked at another experimental paper where they have experimentally generated two different entangled photon states. So it's a continuous variable bipartite systems, two states that are frequency combs with finite width peaks have been identified experimentally using an interferometric setup. And I've given you the reference there, N. Faber et al. So we've identified an appropriate tomographic slice and computed a tomographic entanglement indicator. These are called chronocyclic tomograms, frequency and time, the conjugate pairs. They are the analogs of X and P in this case. And you can see, you can distinguish between the two entangled states. The first is the tomogram for one of the entangled pairs. The second is the tomogram for the other. And you can see the tomograms are clearly different. The spacing is different in the time slice. As I told you, in state reconstruction, people are worried about machine learning because with infinite dimensional Hilbert spaces, the whole thing becomes challenging, state reconstruction. But you might as well do machine learning for optical tomograms themselves. That has been attempted. And we have used the Wasserstein-Gann approach. What happens in the Wasserstein-Gann, Wasserstein generative adversarial network problem is you use a generator, spelling is wrong, and that is trained to reproduce input tomograms. Then there is a discriminator. That is not only trained to reproduce input tomograms, it also examines what the generator puts out and quantifies the distance between what the generator puts out and what the ideal tomogram is. This distance between the two tomograms is quantified using the Wasserstein-based algorithm. Then there is a feedback loop between the generator and discriminator networks. The discriminator keeps on throwing things back to the generator, gets it to learn better and better, till the Wasserstein distance saturates at minimum value. And successful reproduction of the input tomograms has been carried out for different states. We've just put the paper on an archive and sent it off to a journal. So you see, these were the input coherent states. By now, I think you can recognize a coherent state tomogram. This is the sample training input to the discriminator. And these are the generated tomograms. And from these, we have quantified the state, its squeezing properties, not just for the coherent state, for photon added coherent states, for the photon number states, and so on. And done a successful training program. I could summarize now. I believe my time is really up. So I was trying to present a unified framework to examine classical and quantum physics through the tomographic approach. The emphasis is on the importance of identifying and characterizing a state of light from its optical tomogram itself, avoiding reconstruction. Examples of both qualitative and quantitative identification of photon addition and subtraction to light has been given. Tomographic markers like the Wasserstein distance, Kullback-Liebler, and Bhattacharya distance have been introduced. There is excellent agreement with experiments on revival phenomena, also with indicators such as the entanglement indicators from tomograms. The machine learning for optical tomograms of known states has been done as proof of concept and as a precursor to machine learning for characterizing unknown states of light. I will stop here. And if there are any questions, I can take it up.
Thank you, ma'am. Thank you, ma'am. It's a wonderful talk and very illuminating. First of all, I have jotted down a few of my queries which I'll be asking you. But before that, I'll ask the participants if you have any questions. You can ask. You can raise your hand so that I can unmute you, and you can ask your questions directly to ma'am.
Yeah, Shuvik, Professor Partho Guho,
Yeah,
you got some question.
Okay. Just
Please unmute.
give me a minute. Okay. Yes, sir. You can go ahead. Partho Guho, sir, please ask your question.
You unmute him.
Yeah, I have unmuted him.
Hello, can you hear me, please?
Yes, I can hear you.
Oh, thank you, ma'am. That's a wonderful talk. Very, very illuminating. And I must say that I didn't know anything about these tomography things, but I enjoyed very much for several reasons, because it intersects many other areas which I'm interested. So first of all, you use tacitly radon transformation, isn't it? That's one of the
Yes.
thing.
No, from the tomogram to the Wigner function, it's an inverse radon transformation.
Yes, you're doing these things, and because radon transformation is a big thing, and either it comes in a Penrose transformation or any algebraic geometric also, very ways. Number one. Number two thing is that is basically you touched a lot of things with the Weierstrass distance function, with basically optimal transport theory that we work on. Number one. Number two is that you also take a lot of things with the Bhattacharya distance functions, Klubner-Leibler distance function, Bregman divergence functions, well, many other things. We all know from statistical manifold theory, information geometries, and others. I would be obliged and grateful if you give me some references. I have to take, of course, I will look at your paper, but which will directly deals with the things with this the tomography and the statistical manifold or information geometry, because I come information geometry from various different direction. As you say, that machine learning is obviously, but it's before that it actually a geometry of the non-equilibrium thermodynamics, open systems, all sorts of things. I'm leaving to you now. Thank you very much.
Thank you very much. I will certainly give you a set of references, but how do I put it down? I'm not particularly savvy about, getting into the chat box and putting it down now. Perhaps if you can share your email with me, I can send it to you after the talk, after this is over. I will certainly give you a set of lovely references. First of all, the Manco papers, which I have really fallen in love with them. And that sets the base for this tomographic approach extremely well. And then, of course, any usage of the Bhattacharya distance and so on, not just in the context of tomography, but wherever I have seen it. I think that should fit the bill for you. You could get back to me later and ask me for more pointed references, and I'm sure I'll give you if I know of it. Thank you very much.
Thank you very much. Thank you so much. Okay.
Can you hear me? Are you people there?
Yeah, I'm satisfied. Thank you so much. Thank
right.
you. I will go. I'll get in touch with you.
You heard me. All right.
I'll get in touch with you. Definitely. Through Shobika, definitely. Thank you so much.
Okay, any other questions? Oh, here is a question from my part, madam.
Yes.
Can this is written in chat box? Is it visible to you? Can this damping of a system?
Just a moment.
Can the damping of a system be incorporated in a tomogram?
Wait, let me just look at your chat box. Your chat box says, can damping of a given system be incorporated in? Yes. We have looked at amplitude damping and phase damping models. And we have followed the way specific tomograms have evolved under different Hamiltonians. Of course, when you damp, you have to be more careful because the tomogram becomes blurred. And you have to do your readings from the blurred tomograms. But that really helps because an experimental tomogram is going to be blurred. It's not an ideal tomogram. You can incorporate this. You incorporate the damping into your model, which mimics the experiment. Or if you don't have an experiment, if you simply have a theoretical model, that too is all right. You incorporate the damping into the model. Normally, we have used only amplitude damping and phase damping. Then the tomogram can be created, and you follow the tomogram either in dynamics or otherwise. And certainly, you can look at all the characteristics. The variance in higher moments and so on, the formulae don't change. your answers will change because of the damping. It can be done.
Okay, thank you.
I think somebody has raised his hand.
Shobhik, you are not audible. Shobhik?
Yeah. Okay, sorry.
Yeah,
I actually muted myself. We have
okay.
Professor Mohammad Manirul Ali with us, who is going to ask you a question. He's from Chennai Institute of Technology.
Okay.
Manirul, you can go ahead. Hello, you are not audible. You unmute yourself. Yeah.
Hello.
Yeah.
Yes.
Audi-
Good evening, ma'am. Thank you very much for this nice talk. So I have a very small question that during the discussion on entanglement, you have used the subsystem linear entropy. So is there other way also, like calculating other kind of like von Neumann entropy that you used in qubit system? So von
Uh,
Neumann entropy can be calculated using covariance matrix, for example, for continuous variable system.
Yes, we have calculated the subsystem von Neumann entropy also. Whenever we
Okay.
do subsystem linear entropy, we also do subsystem von Neumann entropy. The trends
Okay.
we
Okay.
are the same. We have checked that the trends are the same for the systems we have considered. But we have worked with spin tomograms where we have worked with concurrence, negativity.
Ah,
Because you
ah,
see, I got some experimental data from Professor Mahesh of Ayuka Pune.
ah,
He was in NMRs. So he gave me some spin tomogram data on molecules that he has worked with. And those it was a tripartite system. And then we had to, we looked only at, we divided it as bipartite. The tripartite was ABC, and we either took AB as one subsystem and C as the other, and so
ah.
on. So AB itself is a mixed state because I would have traced out C.
Trace out the other. Yes.
So I'm looking at the entanglement between A and B. So I'm looking at an entanglement for an already mixed state.
Ah, ah.
So there we found that we worked with negativity and so on, and it worked nicely. Yes, we have worked with a variety of entanglement indicators. Always our
Okay.
topographic indicator is compared with a reasonable, well understood indicator, which is got from the density matrix. Yes,
Okay, ma'am. Thank you. Thank you so much.
welcome.
Uh, is there any other question? Who wants to ask question? Can please raise his hand. Uh, if if not, then ma'am, I have written down two or three questions, which I'm going to read it out because since there are more than one question, so I have noted down somewhere. The first question is that in practical quantum information protocols, does working directly with tomograms offer any computational advantage or experimental advantage compared to density matrix based approach?
Only if you're doing quantum information with optics and not with polarization qubits of the photon. You see, as long as
Okay.
your linear vector space is small dimensional, if finally your problem is with qubits and qubits, then you really
Hmm.
can easily get the density matrix. There is no problem.
Hmm.
The problem is
Hmm.
if you use quadrature variables like CVQKD or something like that, continuous variable quantum key distribution, then yes, you are invoking the quadratures. Then the
Hmm.
tomogram is very advantageous.
Okay, understood. And next question that I'm going to ask is that can features of the optical tomogram be used to directly quantify non-classical resources like entanglement and or coherence without going through state reconstruction?
Yeah, I think so. That is exactly what we have tried to do in all these cases. Yes.
Oh, okay. Okay, thank you, ma'am. Is there any other question from the participants? Please raise your hand and ask. So if not, then ma'am, please, you can you I mean or switch on your video so that we can take a picture of
I'll try.
yeah, sure. Thank you, ma'am. And I have taken the snapshot. And first of all, I'll request you to share your, if you do not have any problem, you can share your PPT with me so that I can share with.
You definitely do that. I'll do it with your email.
Yeah, you can send it to my email, no problem. And you can send it to Cassie Lab's email also, or Surajit's email, whatever
All
it
right.
is. Okay.
I'll
So we are actually at the end of the session, and I'll request Professor Ratanu Nath to give concluding remarks for today's session. So Ratanu, it's over to you.
Thank you, Shobhita. Respected Professor Lakshmibala and everyone present. On behalf of CASILab and the Saturday online seminar series, I'd like to sincerely thank Professor Lakshmibala for today's talk. The topic is quite deep and quite detailed, technical actually, but the way you explained it thoroughly, it made it possible for all of us to follow the main ideas somewhat. You built things up clearly from the basics and connected them to experiments, which made the session very meaningful. I'd also like to appreciate the diversity of the audience today. We had senior scientists, researchers, as well as students. It's not easy to address such a mixed group, but your talk managed to engage everyone. The interactive session was also very enriching. The questions and discussions were very engaging, and your detailed responses helped clarify many points further. Thank you again for taking the time to speak with us and for sharing your insights. I also thank all the participants for joining and contributing to this session. With this, I would like to conclude today's seminar. Thank you.
I want to thank you all for a very patient hearing, and of course for inviting me to talk. Thank you.
Thank you, ma'am.
Thank you.
Look forward to more and more such sessions in the future. Thank you so much for joining. Good night.
Good night.